So here we've got a couple other examples of work, and these are going to be similar to what we had with the spring. It's just going to be different kinds of examples. So again, work is still our force times our distance. And in particular, if that force equation is variable, it's going to be the integral from a to b, so where we start our work to where we end our work, of that force equation dx. And dx is that distance because we chop up the length that we're going and we get delta x, so that turns into dx. So let's kind of take apart this question that we've got here now that we kind of have those quick reminders there. So it says to lift a crate with a mass of 10 kilograms to the top of a building 6 meters in height. A cable with a length of 6 meters and a mass of 12 kilograms is used. An additional 4 meters with the same density of cable is, I forgot the of cable, is used to secure the crate. Acceleration due to gravity is 9.8 meters per second squared. So that's part of what we have to work against when we're pulling this up. And force is going to be your gravity times your mass, because you've got to, the force that you need to move an object is you've got to push against your gravity and you got to push against mass. So particularly when we're moving, lifting something up versus when we had that spring, we were pushing against it. So we didn't really have gravity because we were pushing parallel to the ground. But here we're going to be pulling something up. So we've got to pull it up enough to get it past gravity, but we also have to pull it up enough that we're also moving the mass. And so how much work is done in lifting the crate to the top of the building? So let's draw a little picture. So I am big on drawing pictures. We've got our building. It's not that high, right? It's 6 meters. It's kind of a short building, but there's our building, and then we've got a crate sitting down here, and we've got a cable, and we're going to use that to pull it up over the building. And I got a little aggressive with my cable. We're going to have it go right to the top of the building. But then we've also got some cabling kind of holding on to that crate down there. So we're going to have the crate plus some cable that we use to secure the crate. So the things that are going to stay constant on this is the when we're lifting that crate and that cable, this part of it right here, we're going to have to lift that the whole time. We're always going to be pulling with a force to lift that up with our gravity and our mass. So that part of this question is constant actually. So to lift the crate and the cable, holding it, the work that we're going to do there, it's going to be, the force we need to lift up that gravity and also how far we're lifting it. So we've got gravity and our distance. And then what we also need is that weight or mass of what we're lifting. Well, let's take a look at what we're lifting. We're lifting the crate. So the crate, did they tell us how much that weighed? Oh, that was 10 kilograms. Plus, we've got 4 meters of cable holding that crate to our big cable. Well, the cable, we used a mass of 12 grams for the 6 meters. So that 12 grams, 6 meters, that's 2 grams per meter. That's the density of our cable. So we used 4 meters of that. So this is 2 grams per meter times 4 meters. The meters are going to cancel out and they're going to give us that cable is 8 kilograms of mass. So our total weight of our crate and our cable, so again, just this part we're highlighting, not the cable that we're using to actually lift it up. This is just our cable to secure. The work to lift this part of it, that's always going to be constant. It's going to be that 9.8 times 18 times 6. So it's going to take, just to lift the crate and the cable that's securing it, it's 1058.4 joules. Now, to lift this, the cable part of this, so now we want to say, okay, how much is it going to take to lift this part of it? Because we have to work to lift that cable. That cable has weight. It's 12 kilograms, that cable. But as we lift it, we're lifting less and less cable. So as we lift this, we are lifting less and less cable. So the work that's required, the force that's required to lift that cable, it's going to get less and less. Like, it's going to get easier to pull it up as we get it higher and higher because there's less weight that we're pulling. So how we're going to view this is that we're going to set this kind of on an x-axis on the side, that the top is going to be 0, the bottom is going to be 6, and we're going to be moving this up. So our work to move the cable, so this is a work for the lifting cable. And, we are simplifying this a little bit. We're not taking into account that, like, the crate has any height or anything. Just kind of assume that it's sitting at ground level. Maybe it's in a hole. Like, we just need to kind of push that off to the side a little bit. So we're probably going to get a little bit of an overestimate on actually how much work is being done, but that's okay. That's all right. So the question is how much force are we using to lift this cable? Well, the force, let's maybe put it over here because we need to take the integral of that force function. So the force here, so it's still going to be that 9.8 because we've still got to deal with that gravity, right? But then the question is, okay, how much are we using to lift each little piece? Well, we can chop this up, right, like we do, and say, okay, to just lift it that little bit, what's it going to be? Well, its distance that we're lifting there is delta x. And then we can also say, well, we're lifting it some x sub I star, but it's also times our density, and that's going to give us our weight because it's how much of that cable that we're lifting. So we'll pick a spot again in our interval. So like maybe right there is x sub I star. Maybe it's the midpoint of our interval. And we'll multiply that by our density that we figured out over here of our cable. So that's how much of that cable that we're lifting over that distance. And that's our delta x. So actually this is not our force, this is actually our work, our force part of it. It's this part right here. There's force, because I actually grabbed distance in there. And so this actually sets up our integral for us, that it's going to be 9.8 times 2x dx. And, again, this is something that we can do. We've done all sorts of integrals like this before. We actually get 9.8 times x squared because we end up dividing by 2 from 0 to 6. And this ends up being 352.8. And again, this is joules. And so now to get the total work done, we'll take that crate and cable amount that we got plus our variable cable, add those together, and we get 1,411.2 joules to lift this whole thing up. So let's take a look at another example. We're going to look at one where we're pumping water out of a tank. So if you need to copy more of this down, make sure that you hit pause. And let's take a look at an aquarium that's 2 meters long, 1 meter wide, and 1 meter deep, and it's full of water. So we'll draw a little picture. Again, these pictures don't have to be fancy, but they are helpful to think about, that we're slicing things up and what's going to be the area or the volume of a slice. Ooh, we'd be able to see that. I don't know why I always feel like my 3D pictures have to be like so perfect there. And then we'll draw some water here. So we got water there, it's full to the top. And then label wise, it's 2 meters, 1 meter, and 1 meter. and we want to pump out half of the water. So we want to basically get to this line right here. We want to go from, 0 to a half there. So 0 water pumped out to half of the water pumped out there. Well, what are we going to look at? We're going to do what we always do with this. We're going to chop this into slices. So we're going to look at a slice of water, and that kind of feels a little weird, but it's what we need to do. So a slice of water. Oops, my slice got a little wonky there. I keep saying wonky too today. So again, we can set this up on sort of any kind of axis that we want. So we can have this be change in x. So this can be dx, or, while we're kind of setting this up, delta x. Dx and delta x are the same thing. So each slice has thickness of delta x. And then also, if we look at the depth of this, that's going to be x sub I, and we'll put a little x sub I star. It is sitting at a depth of x sub I star. So again, because we're chopping up, this interval here. And again, our depth is going from 0 to 1/2. We mentioned that before. So the volume of a slice, is going to be 2 times 1 times delta x. So again, it's like we've got the base, right? So 2 times 1, and then our height there is delta x. And let's see, what's next? What's the mass of each slice? Because we also need the mass. Let's grab another color. Oops, I left E off volume. That's bothering me. And then I started to write mess instead of mass. Oh my gosh. Mass of a slice. Well, that's going to be our density times our volume, because our volume up here is 2 delta x cubic meters, right? Because this is meters, meters, and even delta x is meters. So 2 times delta x meters cubed. So our mass of our slice is 2,000 times delta x kilograms. And now, again, we still have gravity because we're trying to pump this out and over the side, and that's still 9.8 meters per second squared. And so our force that we're using here is that we've got to overcome that gravity, and then we have to pull up this mass that we have. And then we're lifting distance is, so again, if we go back up here, that work is force times distance. So then we'll go back down here. Work is equal to force times distance. The distance that we're lifting each of our slices, look back up at the picture because I'm circling, it's x sub I star. That's our depth. That's how far we have to lift it. So we're going to get 9.8 times 2,000 times delta x times x sub I star. And this is work, but this is work for one slice. So one slice. So of course, what are we going to want to do? We're going to want to add up our slices. Oh my gosh, it's like we do the same thing every time that we've got the summation of each of these things, and we've got delta x, and then if we make our slices smaller and smaller, so if we take the limit as n goes to infinity, and again, back up here at the volume, that's not going to change the base of our slice, it's going to change the thickness, and that's where our delta x comes in. So because making n go to infinity is making delta x go to 0. And this is going to be the integral from 0 to 1/2 of this 19,600 x dx. So we've got that force function, and that's what we're taking the integral of. And let's see here, what do we end up with? 19,600 divided by 2, x squared, 0 to 1/2. And I assume you guys can plug in these numbers and you get 2,450. And again, this is in joules.